So we probably need to talk about some practical implications of the central limit theorem, right? All this stats theory is great, but the question is, how does that help us? Why do we care? And we care in particular because it permits us to estimate the population mean, right? Because the central limit theorem tells us that the sample mean is an unbiased estimator of the population mean. So look, both of those words are important. It's unbiased. What does that mean? It means that there is the only error involved between the sample mean and the population mean. So, well, I guess let me back up. Any difference between the sample mean and the population mean, we consider to be error, right? It's something that came in that's potentially sampling error, right? That just comes out of the fact that I happen to take a sample, and it's going to be just by random chance a little bit off from the population error. And when it's just random chance, that means it's unbiased. That means over lots and lots and lots and lots and lots and lots and lots of different samples, that goes to zero, that I end up with no error, right? Because sometimes I'll get a little positive error, sometimes I'll get a little negative error, they cancel each other out. It's an unbiased estimate. Now, the downside is we only do it one time, right? We don't take lots and lots of samples, we're just taking one sample. But at least we know that that sample is going to be unbiased, and any error that separates our sample mean from a population mean then is going to be random and is due to random chance, not to any systemic problems. The other piece then is estimator, right? That's important too. This is an estimate of the population mean. It's not the actual population mean. If I knew the actual population mean, I wouldn't need to take a sample, right? And so how do I get an exact instead of an estimator? Well, I could take the mean of the entire population, which is useful if I have a very defined population, but oftentimes I don't. Oftentimes I'm just taking a sample from which I'm trying to infer about a population. So this is ultimately just an estimate, which means that really what I'm talking about here is I can use that sample mean to construct a range in which I'm confident the population mean exists. Right? So I can't necessarily, because it's just an estimate, I can't just say, well, the sample mean is the population mean. These two things are the same. What I can do is create kind of a range of values in which I would say the population mean is somewhere inside of here. And we call that then a confidence interval. Right? The confidence interval in this sense is an estimate of the population mean. And the confidence interval is just our sample mean, right? And this is the confidence interval of the population mean. So where do I think the population mean is? The confidence interval is the sample mean plus or minus a margin of error, right? So the example for this is if I have a sample mean of 10, right? So I took a sample of 10 people out of a population and their mean on some variable was 10, and I decide that a margin of error, right? So this is arbitrary at this point. We'll get to how we calculate this, but arbitrarily I decide the margin of error is 5. Then the confidence interval is 10 minus 5 to 10 plus 5, or 5 to 15. This tells me that the population mean is somewhere between 5 and 15, or at least it's within that margin of error. That given the margin of error I've decided, the confidence interval is between 5 and 15. Now note that the smaller the margin of error, the smaller the confidence interval, right? If I had said a margin of error of 10 instead of 5, then my confidence interval goes from 0 to 20, right? 10 minus 10 is 0, 10 plus 10 is 20. On the other hand, if I went in the other direction, I said I want a very small margin of error, I could say, okay, the margin of error is 1 then. And now my confidence interval goes from 9 to 11. So before we get into where the margin of error, how I determine the margin of error, just from an arbitrary standpoint, a takeaway here is that margin of error changes how sure I want to be. So my arbitrary decision on a large margin of error means that I can be more confident that the true population mean is inside that estimate. On the other hand, if I arbitrarily decide that I want a smaller margin of error, then I'm going to be less confident that the true population is in the estimate compared to that larger one. So not 100%, but there is some arbitrary nature to determining the margin of error. So I guess this really gets us to the next question is, okay, how do we calculate the margin of error? Where does that come from? Here's the thing. We know some stuff about the normal distribution. this is where kind of statistical magic happens, right? I know some things about the normal distribution that makes it very easy to use that as a useful tool, right? Because remember, the normal distribution, right? It's that bell curve where the mean, the median, and the mode are all the same. It's perfectly symmetric. It's perfectly mesocurtic. I know that 68% of the values in that frequency distribution are within one standard deviation of the mean. I know that 95% are within 2 standard deviations of the mean. 99% are within 3 standard deviations of the mean, right? So I know some stuff that can then tell me how confident I can be. If I want to be 68% sure that I have estimated my population mean correctly, which is to say that if I want to be 68% sure that I have constructed a confidence interval that includes the population mean, then I would use 1 standard deviation, right? I'd make sure that my margin of error is 1 standard deviation. And then if it's 1 standard deviation away from the sample mean, then I'd say, well, I'm 68% sure that my population mean is inside of that. If, on the other hand, I want to be more confident, right? If I want to be 95% sure, then I say, well, I want it to be within 2 standard deviations of the sample mean, right? And so I create my confidence interval that way. And I'm just going to plant this seed because it's going to come up on this next slide. Just put it in the back of your hand right now. Remember that remember Z from some before, we talked about what a Z-score was. A Z is an index of how far away from the mean I am in terms of standard deviation units. Just hold on to that. We'll get to it. So here's the thing, though. We're going to use the standard error of the mean to calculate our margin of error. The standard error of the mean, that is a term of art, that it's a number that is derived from the distribution of sample means in the population, right? So again, remember that the central limit theorem tells us that even if the population itself is not normally distributed, the distribution of sample means will be normally distributed. So go back, review again the central limit theorem if you're confused about the difference between the distribution of the population and the distribution of the sample means in the population. Because what's important out of the central limit theorem is the fact that even with a non-normal population, the distribution of sample means is going to be normal. Now, this also happens if we have a very large N. So this is what's going to happen. Also, if the underlying population is normal, right, then it falls out. We don't even need a large N in that case. But with a large N, by large here, we usually mean like an N of greater than 30. What we find is that this distribution of the sample means is normal. Doesn't mean that the distribution of the population itself is normal. Doesn't mean that the distribution of the sample that we took is normal. It means that the distribution of the sample means for all of the possible samples for that sample size is normally distributed. Again, this is central limit theorem stuff, right? So that comes out of that. Well, if I know that the distribution of the sample means is normally distributed, and I know that I can build margins of error off of the normal distribution that tell me things about my confidence level, then this is a super useful thing. And so the thing that gets us to the next step then is that we know, again from the central limit theorem, that the standard deviation of the distribution of sample means in the population is the standard error, right? It's not the standard deviation of the sample, right? It's not the standard deviation of the population. It's the standard error, which is defined by this equation. The standard error is the standard deviation of the population divided by the square root of the sample size for the sample that I took. Right? So remember, sigma here indicates a population parameter rather than a sample statistic. Sigma is the population standard deviation. If I divide that by the square root of the sample size that I took, I get what we call the standard error. The standard error is the standard deviation of the distribution of sample means in the population, which is normally distributed. And so I can use this information to build my margin of error based on the standard error to create my confidence intervals. And that's what I do right here. The confidence interval for a population is the mean of the sample, right? So M here is a sample statistic. This is the mean of the sample that I took, plus or minus some margin of error. Now what I can use is the mean is plus or minus z, right? Remember, z here is just an index of how far away from the mean that I am in terms of standard deviation units, times the standard error of the population mean. Now I substitute in sigma over the square root of n for the standard error of the population mean. That's just plug and chug. And I see now that my formula for a confidence interval is my sample mean plus or minus z, some index of the of how far away I am from the mean, times the standard deviation of the population divided by the square root of n. Right? And remember that z here, I am arbitrarily deciding what z will be. And this goes back to this previous rule that if I arbitrarily decide I want a larger margin of error, which means I arbitrarily decide I want a large z, right? If I want to use a z of 2 or a z of 3, then I'm going to actually have both a wider confidence interval, right? Because now this whole number is going to be larger, which is going to create a larger confidence interval. But it also means that I can be more confident that my population mean is within that confidence interval, right? And doesn't have to be just arbitrary. So earlier I said this was an arbitrary decision. It turns out it's not just arbitrary. The choosing of z is arbitrary, but n also plays a role here, right? So if I have a larger sample size, you'll see that since the sample size is in the denominator, the larger the sample size, the smaller the margin of error. So for a larger n, then I have a tighter confidence interval at the same confidence level, right? So my confidence level, right, am I 95% confident, am I 99% confident, am I 68% confident, comes from z, right? If I want to be 68% confident, then I use a z of 1. If I want to be 95% confidence, I use a z of 2 or 1.96. If I want to be 99% confident, 99 some change, then I use a z of 3, right? So that's the confidence level. If I hold that constant, right, if I don't change z, then if I get a larger sample, I will, at the same confidence level, have a smaller confidence interval, right? Alternatively, if I can't change my sample size, I can change the confidence level, will make that confidence interval larger or smaller, wider or tighter in order to maintain that same confidence level. Here's the thing though, this is the wrench I'm gonna throw in the works. So if we look at this equation, right, the confidence interval, which is just, you know, my confidence interval estimate of the population mean is equal to the sample mean plus or minus z, my arbitrarily decided index of how confident I want to be, times the population standard deviation divided by the square root of the sample size. Well, the population standard deviation, if I know the population standard deviation, there's a really, really good chance I also know the population mean, and I don't need to estimate it. This is dumb. So that's a problem. Now, for large samples, that's not actually an issue, right? For large samples, it turns out that I can just use the sample standard deviation, right? And so I took a sample, I have a sample mean that I'm using in this formula. The sample standard deviation, I can't use that in this formula, except that I know that with a larger sample size, close enough is good enough, and I can just use the sample standard deviation in order to, as an estimator for the population standard deviation. For smaller samples though, which is a lot of times where we work, for smaller samples, I have to make a correction. And so there was this guy named, well, his name was William Gossett, but he published under the name of Student. And he created this idea of, instead of the Z distribution, maybe we should have a T distribution, right? And actually there are many different T distributions, but what he said was he created this index T, which is very similar to Z, except it takes into account the smaller sample sizes. And it takes into account the problems of trying to estimate the population standard deviation from the sample standard deviation, because there's a little bit of bias in there. So we can substitute in the sample standard deviation for the population standard deviation in our confidence interval equation. But when we do that, instead of using Z in our equation, we're going to use T, right? And so what we end up with is our confidence interval, which remember is an interval. It's a range over which I'm estimating the population mean to be. I construct this confidence interval from the sample mean plus or minus t times the standard deviation over the square root of n. Now, t will come from a table, and that'll be in a different video from this one, but t will come from a table. I need two arguments going into it. One is what we call the degrees of freedom. More on that later, but the degrees of freedom, which for one sample is just n minus 1. And then the question of how confident do I want to be, right? There's that arbitrary piece to it. So there's two pieces of information that are going to determine the size of our confidence interval around the sample mean. One is the number of degrees of freedom, which comes from the sample size. And the other one is my arbitrary decision about how confident I truly want to be.